Coulomb's law describes the electrostatic force between two charged objects. It states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Mathematically, it is given by F equals K, frac Q_1 Q_2 RA, where equals electrostatic force in newtons N, equals Coulomb's constant, equals magnitudes of the two charges in coulombs C, equals distance between the charges in meters M. Important points. If the charges are like charges, both positive or both negative, they repel each other. If the charges are opposite, one positive and one negative, they attract each other. Coulomb's law is similar in form to Newton's law of gravitation, but applies to electric forces instead of gravitational forces. Coulomb's law describes the electrostatic force between two charged objects. It states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Mathematically, it is given by F equals K, frac Q_1 Q_2 RA, where equals electrostatic force in newtons N, equals Coulomb's constant, equals magnitudes of the two charges in coulombs C, equals distance between the charges in meters M. Important points. If the charges are like charges, both positive or both negative, they repel each other. If the charges are opposite, one positive and one negative, they attract each other. Coulomb's law is similar in form to Newton's law of gravitation, but applies to electric forces instead of gravitational forces.
Example of Coulomb's law problem. The charges, C and C, are placed 0.05 meters apart in a vacuum. What is the magnitude of the electrostatic force between them? Solution. Using Coulomb's law, F equals K, frac Q_1 Q_2, RE given in square meters per Celsius squared CCM. Substituting the values, F equals 8.99 times 109 times frac 3.0 times 10 minus 6 to 0.0 times 10, 6 0.05 E F equals 8.99 times key E times frac 6.0 times 10, 12 0.0025 F equals 8.99 times key E times to 0.4, F equals 21.6. Text and answer. The electrostatic force between the charges is 21.6 N, and since the charges are opposite and, the force is attractive.
Example 2. Repulsive force. Problem. Two charges, C and C, are placed 0.1 meters apart in the air. What is the magnitude and nature of the force between them? Solution using Coulomb's law. F equals K, frac Q_1 Q_2 RA, given and meter per C, CCM. Substituting the values, F equals 8.99 times 109 times frac 5.0 times 10^6 2.0 times 10 6 0.1A. F equals 8.99 times YY times frac 10.0 times 10 12 0.01. F equals 8.99 times YY times 1.0 times 10 minus 9. F equals 8.99. Text on. Answer. The electrostatic force between the charges is 8.99 N, and since both charges are positive, the force is repulsive, they push away from each other. Real-life applications of Coulomb's law. 1. Electrostatic precipitators, air purifiers. Used in industries to remove dust and pollutants from the air. Works by charging dust particles using Coulomb's law, then attracting them to oppositely charged plates. 2. Lightning and thunderstorms, clouds build up electric charges due to friction. When the electric force Coulomb force becomes strong enough, it ionizes the air, leading to a lightning strike. 3. Photocopiers and laser printers, the drum inside a copier is given a charge. Toner particles stick to charged areas, transferring the image onto paper. For balloon and hair experiment, rubbing a balloon on your hair transfers electrons, making the balloon negatively charged. The charged balloon then attracts small pieces of paper due to Coulomb's force. 5. Static shock from touching a doorknob. When you walk on a carpet, you accumulate charge. When you touch a metal object, the charge is transferred suddenly, causing a small electric shock. Which application would you like more details on? Here are some options. 1. Electrostatic precipitators, how they work to clean air in industries. 2. Lightning and thunderstorms, the role of Coulomb's law in lightning formation. 3. Photocopiers and laser printers, how electrostatic forces help in printing. 4. Balloon and hair experiment, a simple experiment with static electricity. 5. Static shock, why you get shocked when touching metal after walking on a carpet. Electrostatic precipitators, air purifiers, and Coulomb's law. What is an electrostatic precipitator? An electrostatic precipitator (ESP) is a device used to remove dust, smoke, and pollutants from industrial exhaust gases before they are released into the air. It is widely used in power plants, cement factories, and steel industries to control air pollution. How does it work? The operation of an ESP relies on Coulomb's law, which governs the attraction and repulsion of electric charges. The process involves four main steps. 1. Charging the dust particles. A high-voltage electrode inside the precipitator emits electrons' negative charge. As dirty air passes through, these electrons attach to dust particles, making them negatively charged. 2. Attracting the particles to plates inside the ESP. There are large positively charged metal plates. According to Coulomb's law, the negatively charged dust particles are attracted to these positively charged plates. They stick to the plates, separating from the air. 3. Dust collection. Over time, the collected dust forms a thick layer on the plates. The plates are periodically shaken by mechanical vibration or electric discharge, causing the dust to fall into a collection bin. For clean air release, once the dust is removed, the clean air is released from the system into the atmosphere. Why is Coulomb's law important here? The electrostatic force given by ensures that even tiny dust particles are strongly attracted to the plates, making the process highly effective. The distance factor is important because the force increases as the particle gets closer to the plates. Advantages of electrostatic precipitators. Highly efficient, can remove over 99% of dust and pollutants. Handles large volumes of gas, useful for industrial applications. Low maintenance cost. Unlike filters, ESPs don't clog easily. Where are they used? Thermal power plants, to remove ash from coal combustion gases. Cement factories, to trap fine cement dust. Steel and metal industries, to reduce metal oxide emissions. Here's a simple explanation of an electrostatic precipitator ESP with a diagram. Diagram explanation. 1. Dirty air inlet gives air containing dust, smoke, and pollutants enters the ESP. 2. Charging section gives a high-voltage wire-negative electrode emits electrons. These electrons attach to dust particles, making them negatively charged. 3. Collection plates gives large positively charged metal plates attract the negatively charged dust particles due to Coulomb's law. 4. Dust removal gives the plates are periodically shaken to drop the collected dust into a bin. 5. Clean air outlet gives the cleaned air is released into the atmosphere. Simple ASCII diagram of an ESP. Plus electrostatic precipitator plus a plus. Dirty air gives equals greater than plus gives clean air. Charging, collection, wires, plates. Here is a schematic diagram of an electrostatic precipitator ESP showing how it removes dust particles using electrostatic forces. Let me know if you need any modifications or further explanations.